Okay, so we've been doing linearized flow, right? And the primary reason for doing linearized flow is what? Okay, we have exact equations which are very large. Okay, so and then we said no, we're going to linearize this, use small perturbation, right? And then we're going to use linearized equations. So essentially, what do you think is the reason for that? The main reason to do that is for simplicity, right? For simplicity, it's just too difficult to solve those equations, and even if we do, how do we validate them, right? That's the main concern. So if we can do with something that at least we are sure of, we're kind of better off. Okay, so let us see something a little more interesting. Okay, in terms of linearized flow. Okay, this is well, you could say today's class is about similarity rules. So we'll see what I'm talking about. Okay, we will do a transformation in space, and space meaning in domain rather x y to another to transform it to another domain of space, and then see that what linearization actually does. Does it simplify, or does it have any more physical meaning, or what happens? Okay, so linearization, of course, when we say linearize, we're basically saying we are bringing in some simplicity in the way we solve our numerical equations, governing equations, solutions to them. Okay, so and the physical analogy to that is that we basically if you assume small perturbation, then that results in linearizing the equations, the numerical part becomes simplified. Okay, so like we've done earlier, right? So we had for 2D subsonic flow, right? So if you remember, right. So this was our governing equation. Solve this now. This phi p is the perturbation potential, and you can see that this is in our usual x y or Cartesian coordinate system. Okay. Now, so we have this in our okay. So let us do this here. So essentially, what I'm saying is that. So say we have right. Say we have an airfoil like that. Okay, in this x y coordinate system, then the governing equation for a 2D subsonic flow will be so. Okay. So phi p and perturbation potential, and if I know the perturbation potential, I should be able to find out the velocities and so on and so forth, and hence the properties. Okay. Now let us use, say, what if instead of this x y coordinate system, what if I change the coordinate system a little bit? Now let us I just assume this. Okay. So let us say we will change this coordinate system to something like this. Okay, so it's a orthogonal system. So similarly, so I'm just, if I change the coordinate system to say something like this, there are two questions. Now, what exactly is the transformation? What is the connection between the relation between x and z, and what is the connection between y and eta, right? And what happens to this shape? How does this airfoil look in this coordinate system? How does this look in this coordinate system? Okay. And another question is, what happens to this equation? This is the governing equation in the x y coordinate system, and how does that change over in this coordinate system, right? So these are some of the questions we'll try to answer. Okay. So, having said that, let us use now let here we are going to just denote, we are going to just denote the lambda square to be equal to this. Okay. So, therefore, our governing equation basically becomes this is I am just writing the governing equation in the xy coordinate system in this form, right. Now, if I do that now, so therefore, like I said, the relation between x and z and y and eta. Okay. So, let us use this transformation. So, let us use this transformation where we say that x is the same as z, but okay. So, essentially what you are saying is that z is the same as x, but eta is equal to lambda into y, okay, where lambda is this. Okay. So, this is a transformation that we are trying to use here. Okay. So, if I do that, right, if the y axis is somewhere connected to the free stream Mach number, okay, in this fashion, and z axis remains as it is, then two questions. One is what happens to the airfoil shape in the xy axis? How does this transform into this space? Number one, and number two is what happens to the governing equation? How does this look in this transformed space? Okay. Let us see. So, since we have this here, right. So, therefore, what we will say now, we are writing the governing equation in terms of a perturbation potential. Okay. So, therefore, so let us call say this equation as 1, right. If I do that, okay. So, now using this transformation, of course, if I use this transformation, then I am going to denote this as a bar. Okay. Right. Let us call that as 2. Okay. So, basically what we have here is that this is our the perturbation potential, and the way I denote that here is by bar, and what I note is that this is equal to right, or let us say I will write it this way. Right. So, this is basically the transformation. So, now let us do some math with this. Okay. So, now if you look at this, so we said that x is this and eta is equal to lambda y. This is our transformation. Okay. So, if that is true, then what we get is what is this? Del z del x is 1, right. If you look at this, if you do the math from here, then is of course 0. Okay. Del z del y is of course 0. So, what I note here is the relationship or change of z if I change x or y. Okay. Similarly, let us do the same for eta. Okay. For eta, del x is 0 and del eta del y is equal to lambda, right. So, this is basically the change in the coordinates, transform coordinates with respect to the Cartesian coordinates or the original coordinate system that we are using, right. If I do that, so then now phi px, okay, now phi px. So, or this is not, this is what? This is basically right. So, then this I can write, if I write this in terms of the potential perturbation potential in the transformed coordinates, right. So, this is this, isn't it? This is what this is all about. Now, if I were to write this more clearly, you can see that this is this. Okay. Now, this is in the phi p is essentially in the x y coordinates, okay, and this is in the zeta eta coordinates, and I need to take the del x of this. Okay. Okay, so basically what we are saying is this we can write as del x of phi p theta this. Okay. So, the way we will write this is like this. So, we are basically going to take a change of this perturbation potential in the transform coordinates with respect to x. So, that would mean that we need to also check, we need to take that change with respect to the change in coordinates z and eta with respect to change in x, right. So, therefore, what I can write here is, so I take this out here. So, this would mean del zeta into del zeta del x, right, plus the change in del eta right, makes sense. So, what we are writing here is we are writing phi p x, okay. So, which is essentially del phi p x, okay, with respect in the x coordinate. So, then I write that in terms of the perturbation potential in the transformed coordinates here, okay. So, which is essentially this, okay. Now, so I say transformed coordinates with respect to change in x, right. So, which means that if you change x, we need to take the change in phi p where with the change in z as well as the eta coordinates. Okay. Now, as we have just seen, now if you look at it, del z del x, this is 1, right, this is 1, and del eta del x is 0. So, then this is 0, right. So, what we essentially get over here, so therefore, so you can say phi p x, okay, is equal to 1 by lambda right. So, you can write it like this phi p zeta, or this is nothing but del z, isn't it? So, therefore, this as, let me call this as equation 3. Okay. So, phi p x is nothing but phi p z by lambda. This is the transformation. So, del phi p this, okay, just this term out here, just this term del phi p bar del x. Now, that is what we expanded in this bracket here, turns out to be del phi p bar del z. Okay, there is really no difference. Okay, so therefore, let us write that down as well. Okay, so we can write that down, that del phi p bar, okay, del x is equal to del phi p bar del z, and let us call that as 4. So, we basically get 2 information here. So, what we get is a connection between the del phi p del x and del phi p bar del z, and also del phi p bar del x is also equal to del phi p bar del z. Okay. So, essentially having done that, okay, so let us using this, okay, so phi p x x, which is nothing but right. So, if this is it, so what this is nothing but del del x, okay, of phi p x, right. And as we have seen from here, okay, if I were to write this in the phi p bar, then the way I would write this is okay. So, this is what we get here, right. So, then, so this what we get here is this, and we get del del x of phi p z, okay, phi p z. Okay. Now, as we have seen over here, you can see this phi p del x of phi p is equal to del del phi p bar of del z. So, then again we can also write this as, so therefore, so we can write this as 1 by phi right. So, okay, and let us call this as say 5. Hopefully, you got this one right. So, what we are doing here is taking del 2 del x 2, right. So, we write this, okay. So, phi p x I write in terms of the z, okay, here, and what we have seen here that this is phi p x, okay, is equal to phi p bar z. So, this phi p x, this phi p x you can also write as phi p bar z. Okay. So, therefore, if you do that, so essentially what we have here now, okay, is that del del x of this, okay, which is again the same as del del z of. So, therefore, this actually you can write this as, okay, one more the bracket, this also you can write at del del z of phi p z. Okay. So, you can write that. So, therefore, what we get is this relationship for the second order derivative. Okay. So, we have this here. So, having done that, obviously, now we will do the same thing for phi p y and phi p y y. So, without sort of okay. So, let us go ahead and do that. Okay. So now, okay, so if I do that, right, so phi p y, which is nothing but, right, so del y, okay, so this I can write as del phi p, okay, so this is del y of 1 by lambda bar phi p, isn't it? Bar phi p. So again, if I expand this, okay, if I expand this, so essentially what I am getting here is 1 by lambda del phi p bar del y, right. Now let me go ahead and expand this. So what we get here is that this is what we get. Now del phi p del z del z del y, okay, then plus del eta del y. So basically we are tracking the change of the perturbation potential in the transform coordinates with respect to the change of both coordinates with respect to y, okay. And again, as we have seen before, del z del eta. So if you look here, del z del y, which is 0. So del z del y, this is 0. Del eta del y, if you del eta del y is equal to lambda, right. This is equal to lambda. So what we get here is that okay, phi p y is equal to, this lambda cancels out. So what we get here is phi p bar eta, okay. So we can call this as 6, okay. This, and also if you look at this here, del phi p del y, this is just the term in the bracket. So also what we see is that del phi p bar del y, okay. So this del phi p bar del y is equal to lambda into del phi p bar is equal to lambda del phi p bar del eta, and let us call this as 7, okay. So this is essentially the relationship between the perturbation potential in the xy coordinate and in the transform coordinates, and this is the transform perturbation potential transform coordinates, okay, and the differentiation with respect to the y axis and the eta axis, okay. So having done that, so similarly, okay, what we need to get now, phi p y y, okay. So phi p y y is what? Phi p y y. So I can write this, that phi p y is equal to phi p eta, right. So this is okay. So basically this is, so I can write this as phi p eta y, okay. So this is nothing but okay, so this, okay, so phi p eta y, so this is again equal to, right. If you look at this over here, so this term is nothing but phi p eta, okay, this phi p eta, and so I introduce this here. So therefore what we get is okay. So having got all these terms right, okay. So the reason we are doing this, hopefully you can see, because what we are looking to do here is how does this transform into the transformed coordinates, our equation. So, we basically need to get a term equivalent to del 2 phi p del x 2. So, we need to get a term here which is del 2 phi p bar del z 2 del 2 phi p bar del eta 2, right. So, that is why we went about doing all these things. So, let us see how does our equation transform. Okay. How does our equation transform? Okay. So, now let us see. So, we have say let us say erase this. Okay. Okay. So, this is our equation. Okay. So, now here, so what we can yeah, okay. So, we can also write this as lambda square, okay, as we have assumed. So, then if I write this, how does del 2 phi del x 2 transform in the transformed coordinates? So, if you look at this, so this is your del 2 phi del x 2. So, this is this all, or we can write this as lambda square phi x x plus phi y y 0. So, if you look at this, okay, so this is the perturbation potential, of course. Okay. Now, this phi p x x is nothing but 1 by lambda phi p bar z z, right. So, therefore, this I can write so this I can write as 1 by lambda phi p bar c c, right. This, and what happens to the next one, phi p y y. So, let us look here. So, phi p y y is lambda into phi p eta eta. So, again this is equal to lambda into phi p bar eta eta, right. So, this is our xy coordinate system and this is our transformed coordinate system, right. So, when we have this, so now if I write this out, okay, now let us see what we get. So, if I do, so basically this becomes lambda, so the lambda cancels out. So, what we have from here do you recognize this? Let me write this out in another form. Now, do you recognize this? Well, if you are saying Laplace equation, well, you are right. Okay. So, this is therefore our transformed equation. This is therefore our transformed equation, and this is nothing but the Laplace's equation, right. So, therefore, let us say, so this is our equation here, okay, and the governing equation here is lambda square phi p x x plus phi p y y is 0, right. And what we get over here is that here, so in here our governing equation basically becomes phi p bar, or let us just say Laplace equation in phi p bar. Okay, Laplace equation in phi p bar. Okay, now that is very, very interesting. Okay, that is very, very interesting. Why? Because this is a 2D subsonic flow. Okay, 2D subsonic flow. When you see the Laplace equation, what happens to the Mach number? It's not there, right, anymore. So Laplace equation is basically the governing equation for 2D, in this particular case 2D incompressible flow. So therefore, if I transform my space in the way that I have done here, my 2D subsonic flow governing equation actually gets transformed numerically to the Laplace equation, which is the 2D governing equation for incompressible flow. My life gets easier, right? Could have it better. So having done that, having got that out of the way, so the next question to answer is, okay, but what happens to my airfoil? Now does that become a square or a cylinder, or what happens to that? What happens, what kind of shape is it? Because the equation has transformed itself, okay, to the Laplace equation, which is great. Okay, so this phi p, okay, so this is essentially, this is compressible flow here. So this is a compressible flow, right? Okay, so this space is, however, it's right here. So when I transform it here, it becomes incompressible. Okay. All right. Now what we need to look at is, how does this shape change? Okay. So let us look at that. So in order to look at that, let's go ahead and look at a few things. Okay, so if you remember what we did in terms of the boundary conditions, right? So now dy, this is in the xy coordinate system, the Cartesian coordinate system. So this is the physical slope of the body, right? This is the physical slope of the body here. Right, this is dy by dx here, okay, and this was equal to, right, if you remember. So these were the perturbation velocity in the y component, and this, so assuming small perturbation, so which is what we are doing here, linearizing the flow. So what we have is this, right, we had this. So in this case, how does now this transform here? How does this transform here? Okay. So therefore, in this case, yeah, and this also one could write, of course, this one could write as, if I write this in terms of the perturbation potential, then of course I can write it this way. All right. Now, if the like it was for the problem that we had, that the contour was given to us, okay, let this function, let that function be this, let that function be f(x), which gives the contour of the body here. So I could write this, okay, I could write this therefore as equal to, right, just so dy by dx would be the df dx. Okay. So therefore I can write let's do that. So del phi p del y is, let us give the function to be, say y is equal to fx. Okay, let's give the function to be here. When I draw the body out here, let the function be like this. Okay, y is equal to fx, and here, so let that be eta is equal to. Okay, so we don't know how the body will look like here. We still don't know. So let us write that as eta is equal to this one. Okay, so this is basically the definition. So from there, so when I write dy by dx is essentially df by dx. This is what we get in the Cartesian coordinate system. So now we'll do the similar stuff in the transformed coordinates. Okay, so in order to do that, so essentially what we are looking at is right. So this is the the corresponding, so del phi p bar del eta, right. Del phi p bar del eta is equal to, okay, if you look at this particular which we did just now, so del, or this is basically del phi p del y is equal to del phi p bar del eta. So therefore this I can actually, this is actually equal to, from our transformation, del phi p del y is actually equal to del phi p bar del eta. So therefore in this particular case, this is also equal to del this thing, but again eta is equal to g. So del phi p del eta, so which is basically d eta dz. So this also again is equal to right. Again this is what we get. So therefore so from here what we get is del f del x is equal to del g del zeta. Okay. So what does that mean? That this del f del x, okay, del f del x, which is the slope in the xy coordinate is also the same as the slope in the zeta eta coordinates, in the transformed coordinates. So what we are basically saying here, that slopes are, the slopes are same. The slopes are same, which means what? The slope of the body in the xy coordinate system is exactly the same as that in the transformed coordinates. What does this tell us? That the shape of the body doesn't change, which means that here too I have exactly the same shape as we had in the xy coordinate system. Now, isn't that nice? So what we have done here is we've taken the coordinate system, this is the original coordinate system on which we have a body which looks like this, okay, an airfoil, and it is a compressible flow, as a result of which has governing equation is this, right. So what we do is we take the same body which looks exactly the same, but transform these coordinates, okay, into eta and zeta in such a way that zeta is x and eta is lambda y, and the perturbation potential in the xy coordinate is phi p, here it is phi p bar. This is the transformed, this is the relationship with the phi p of the xy coordinate system, and what we see is that we get the same body, okay, we get the same shape, okay, but the equation transforms, the governing equation transforms to the Laplace equation, okay, in phi p bar, which is nothing but the governing equation for incompressible flow. So this like really makes our life a lot more easier, okay, than even with linearization whichever we had. Okay. So, if we do that, now let us also just take a second and write out the expression for the coefficient of pressure in that particular in this case. How will Cp change, okay, from here to here? Now, Cp, if you remember right, Cp was this. So, if Cp is this, what do we get? This is nothing but del phi p del x, right. This is in the xy coordinate system, and what is the connection of del phi p del x with, how does that transform to the zeta eta coordinate system? So, what happens here, this is equal to, right. Now, if you transform this, what you get is right. So, then I am going to write this as, so if I am going to write this, so let me write that as okay. So, if you look at this, okay, so let us del phi p del z. So, this term I can write as basically the u component of the perturbation potential, or the this is basically the the z component of the perturbation potential, this thing. So, this is essentially nothing, I can write this as bar. So, this is the u velocity, perturbed velocity in the z direction in the transformed coordinates, right. So, then I can write this as u bar, and let us just call that as dash, just to denote that as the perturbation potential, perturbation velocity, right. So, this is what we have. So, what we can see here, the Cp, which is minus 2 u dash by v infinity, it has the same form also out here, it has the same form here in the transform coordinates as well, where this is nothing but the perturbation velocity component in the z direction, which is the analogous of the x direction, right. So, therefore, what and now that we have found out, now that we have been able to establish that this z eta coordinate system, basically it is an incompressible flow. Okay. So, then I will write this in a special notation, I am going to call this as basically okay. So, the Cp naught is nothing, is basically the incompressible pressure coefficient, right. So, therefore, for any in the case that we are considering, for any 2D subsonic flow, right. So, this is a compressible pressure coefficient is basically given as 1 by lambda. Okay. So, the lambda is basically the transformation used into the incompressible pressure coefficient. So, Cp naught is basically incompressible pressure coefficient, right, and this, let us call this as okay. And so, what we basically see, okay, that we have the same profile, okay, we have the same body, isn't it, we have the same body, okay, and what we have basically done now is that we have related the Cp in this compressible flow field, okay, to the Cp in an incompressible flow field over the same profile. Meaning, say we have this particular body. In one case, we consider a compressible flow over it. Okay. So, we get a coefficient of pressure which is Cp. Now, consider another case where we have the same flow field, we have the same body and we have an incompressible flow over it, and the corresponding pressure coefficient is Cp naught, right. And what we have just now established is this relationship, which is a relationship between the coefficient of pressure in the compressible flow field to the coefficient of pressure in the incompressible flow field over the same body, over the same profile. Okay. And this is basically credited to Prandtl-Glauert, and this is so Prandtl-Glauert okay. So, essentially Prandtl-Glauert similarity rule. Okay. So, this is the basically this connects the Cp in the compressible and incompressible flow fields over the same body. Okay. So, briefly before we sort of close for today, let us also, I will just write down coefficient of lift. So, taking from taking a cue from this similarity rule, taking a cue from this similarity rule. Okay. So, coefficient of lift is lift by dynamic pressure into an area, and similarly Cm is nothing but this again into because I have m there. Okay. So, in this case also, right. So, Cl is, if I were to write this, what is our lambda? So, lambda and so, basically what we do here, these are the two incompressible Cl and Cm, right, and this is the Prandtl-Glauert correction to it. You can add this correction to it and use it as the compressible Cl and Cm over the same profile. Okay. So, this you can say this is the rule for that matter. So, basically we can use the incompressible Cl and Cm, add a correction to it and use it as the compressible Cl and Cm. So, okay, I think we will stop here and continue this next class. Thank you.